So far we have come across one single surprise in this section. The surprise was that the set of even integers is the same size as the set of all the integers. And there's going to be more surprises coming up in this section, and the proofs are going to get kind of very complicated very quickly. So I'm going to try to show you in diagrams what's going on behind the proof, but you're not really responsible to know this level of proof or be able to come up with functions like this on your own. I just want you to understand what's out there available, because if you're going to take real analysis classes, this concept is going to repeat. So I just want you to have exposure to it at least once so you kind of know what's out there. So the next topic we're going to talk about is countably infinite. So we say that something is countably infinite, or in other terms countable, if it has the same cardinality as the set of positive integers z plus. So to say that something is countably infinite, it just means that you have the same number of elements as the set of positive integers. And when a set is too big, it doesn't have the same number of elements, maybe more, than the set of positive integers, we say that the set is uncountable. So that means that it is not countable. So every single finite set is automatically going to be countable, but this is talking about infinite sets. So, countably infinite just means that you have the same cardinality as the set of integers that are positive. Okay, so let's look at another surprise right now. In this problem, we're going to show that the set z is countable. So again, what we're trying to do right now is show that the set of integers is equal in size to the set of possible integers. So think about that for a moment and let it sink. There are as many integers as there are positive integers. Okay, so how do we go about proving this? In order to prove that, let's look at a diagram first. So this diagram is going to represent all the possible integers. So these are the regular integers that I'm trying to figure out if they're countable or not. And what I'm going to do is develop a way to count these integers by only using positive numbers. If I can do that, then I have successfully shown that there are as many integers as there are positive integers. And so here's how it's going to work. I'm going to start at 0, and I'm going to call him the first number. So he's going to be counted on my first finger, basically. Then I'm going to go to 1, and I'm going to say he's the second one. And then I'm going to go bounce over to the left, and I'm going to count -1, and he's going to be the third finger. And then so on and so forth. So the 2 is going to be the fourth finger, and I could keep doing that all day long, right? And I'm only using positive numbers. The ones in blue are always positive. So after I get to 2, I go across to the other side, and I get to -2. He's going to be the fifth integer. So integer number 5. So I've used one hand so far. And I could go to the other side, and that's going to be the other hand, number 6, and so on. So 7, and then if I go again, I'm going to get to 8, and then I'm going to go again, I'm going to get to 9, then again to the other side, that's the 10th integer, and so on and so forth. So in this way, I can count every possible integer on the number line, and every one of these gets counted using a positive integer always. So the number -6 is going to be the 13th guy that I counted, and then 7 is going to be the 14th guy that I counted, and then I can bounce again over here to the other side and count the number -7. He's going to be the 15th integer, and so on and so forth. In this way, I can count every integer on the integer world once, and I'm always using positive integers to do that. So in other terms, what I'm doing is basically building a one-to-one correspondence from the set of integers to the set of positive integers. And so that means that the two sets have to be equal in size. That's what it means to be countable. Okay. Now, obviously, this is kind of complicated and weird, and you're not expected to be able to do this. This is advanced level mathematics. But there's a function. I mean, this is a diagram that shows you what the function is doing, but there's an actual expression that you can try in order to see that this is actually working. So as a matter of fact, this is the name of the function. It's kind of a piecewise defined function, and it's going from z plus to z. So what is this function doing? Here's what it's basically doing. So it's basically taking the numbers in blue and considering those as your domain. And in return, it gives you a number from under the line, the integer itself. So like for instance, if I want to know what corresponds to 13, first of all, 13 is odd. So I'm going to say, oh, 13 is odd. So what integer corresponds to that? When you're odd, you just take the 13, subtract 1, and divide by 2. So 13 minus 1 is going to be 12. Divide by 2 and put a minus in front, and you get -6, the integer on the bottom. So let's try it out again. What about if I had, for instance, I don't know, 6 as the number? What would come out? It should come out with a 3 at the end. So let's try it out. F of 6, how much is that? Well, 6 is even, so I'm supposed to use the first definition. When 6 is even, I do 6 divided by 2, and then that gives me 3. And 3 is the number that I found on the bottom. So it's the output, basically. So -6 was the output, just like earlier. So it's taking the input, which is a positive integer, and it's assigning to it a random integer that could be positive, it could be negative. So this function can be proven to be one-to-one and onto, although I'm not going to do that here. But because it is one-to-one and onto, then it will be possible to say that the sets z plus and z have the same cardinality, or in other terms, that the set z has the same cardinality as the z plus set. Remember, it's reflexive and symmetric and all that good stuff. So even though I am not showing it, it can be shown that this function is a one-to-one correspondence. So in other terms, this would imply that z and z plus, or in other terms, z plus and z have the same cardinality. So there are as many positive integers as there are integers, which in turn implies that z is countable. So why can I say that z is countable? Well, because if you are in a one-to-one correspondence with the set of positive integers, then you're going to be called a countable set. And that's what's happening in example 2, part 1. Now, let's see, are the set of 2z countable? Is the set of even integers countable? So in an earlier example, we showed that the set 2z had the same cardinality as the set z. And in the last problem, we showed that the set z itself has the same cardinality as the set z plus. So that means by transitivity that the set of even integers is equal in size to the set of positive integers. So this implies that the set of even integers is also countable. And that's what we wanted to do. So there's no reason to develop a new function all over again. You could just say that the set 2z is equal to the set z. We proved that. And then we also proved in part 1 of this problem that the set z itself is equal to the set z plus. So that means by transitivity that the original set 2z and the final set z plus are equal in size, which means that they are countable. Because if you are in equal in size to the set z plus, then you're automatically called countable.